Hello, everyone. Welcome to MODEX Network Voices. We're excited to have you. I'm joined by, of course, Ivan Rupnik. Ivan, you want to say hi?
Hello.
And I'm also joined today by Julian Bowron. He is a longtime acquaintance, and we're excited to have him here to talk about some innovations in the offsite and modular space. As you know, MODEX Network Voices is a discussion. So Julian will be showing some things, and we'll be discussing some of the innovations that in his history and his journey in the offsite and modular industry. So welcome, Julian.
Well, thank you, Ivan and Ryan for inviting me to this. I really appreciate it. So the answer to the question is that my journey into modular construction has really been a continuum. From the earliest stages of it were simply having a desire to be better as a craftsperson in my own work in metal fabricating and woodworking. But in the mid 80s, we began to use CAD/CAM methods quite a bit. So this is at the very beginning of the popularization of that. So at that time, CAD/CAM was huge in aerospace and automotive already, and in the tool and die industry. But it really was unknown in woodworking and metalworking and the architectural fabricating industries. And by 90, we were routinely, designing stuff in at that time, Autodesk software, AutoCAD and so on, and then issuing cut files as DXFs so we were issuing DXFs and, very simple 2D kind of data to people to do CNC punching, and so on. And we actually got into doing a certain amount of 3D printing back then and completed a number of projects, mostly prototypes for drafting instruments. And we did a bunch of work for a Celti Letraset at the time. Remember Letraset? Mm-hmm. They had a line of drafting instruments. And so then so after September the 11th, which was a big hinge point in our business, we decided to place a much greater focus on design, and we moved to SolidWorks as our platform. SolidWorks and CATIA, actually. And our business really interestingly took off at that point. We got an enormous amount of work in New York City, specifically the island of Manhattan, to do a bunch of very complex three-dimensional architectural projects. So, Hilfiger's global flagship, the Feature Stair, the HBO store, Louis Vuitton, my Hennessy Group's headquarters lobby, a ton of work like that. And it culminated in us winning the contract for 50,000 square feet roughly, or 40,000 square feet of washrooms for the Bow in Calgary, a Norman Foster project, all executed as modules. And these modules were, what we would now think of as sort of hotel room size. They were 12 or 13 feet wide, 30 feet long, 10 feet high, all lined in back painted glass and stone and so on. And so at that point, we'd migrated all the way from kind of primitive CAD/CAM to full volumetric modular delivery, and the entire project driven from a computer model. All of the cut files, all of the ordering, all of the project management, it was completely in the SolidWorks in a parametric environment. And when that was, I guess, about 3/4 finished, I sold that company, which we'd been in a partnership with a big structural steel fabricator, the Walters Group, and I sold the company, the last of the shares, to them, and left shortly thereafter. And then, interestingly, leveraged that, I would say, that experience to take up my position at Shop Architects in New York City, who hired me to do a constructability review of the B2 project, B2 at Atlantic Yards. And I think they already had some concerns that the project might not go well, and I was able to, the partners readily agreed to provide me staff and resources to develop an alternative to the structural system that had been developed for that project, which I did. And actually, there were 4 of us on the patent application for that system, which is now referred to as the Vectorbloc system and is being deployed continentally by Z-Modular. And then about, I guess it would be about a year later, roughly, I actually bought out Shop's interest in those patents and brought the whole concept back to Toronto, where we developed it further and went into a second and even a third iteration of the design with refinement at each stage. And that is the Vectorbloc system that's being deployed today. At 5 sites with full robotic implementation and so on, and that company I also sold. So I'd sold out of my previous venture, then I sold that venture to Zeckelman Industries, and then it would be about it's about a solid year and a half ago, roughly. I began on my own to really think about this whole issue of the armature to which all the materials are fastened to make a volumetric module, and I sought to develop a system that was low cost both to make and to use, that would be suitable for mid-rise, low-rise applications, which is of course the vast majority of the market in North America. So the Vectorbloc system is an excellent choice for self-bracing high-rise construction, but I felt that there was an opening in the market for something, let's call it more modest. And so that has now been we started to promote it actively, I guess, about 8 weeks ago. I mean, it was literally the World of Modular convention in March. It's only May. It's amazing how the world has changed and how fast things are moving. And that's where we are today. So as you interview me now, we have offer letters with about 6 different entities in North America who will either be producers of the system or users of the system. We have one licensee on board who has taken a territory in the United States and is actively funding us. And that's where we're at. That's where we're at today.
It's really great to hear, Julian. I think you had some images you wanted to show that kind of tell a little bit about some of those systems you've been working on. Would you mind sharing that for us?
So yeah, I believe it's broadly accepted that the B2 project 461D, it was a real turning point in the North American modular industry. It was an extremely bold project, and kudos to the people that to Forest City for embarking on something so ambitious. A lot of people are critical of this project because, of course, it did take longer than it was supposed to, and it did cost more than it was supposed to, and so on. But the fact remains, it's been an inspiration for many people, and it's been effectively a challenge for many people. And for that, I think we all should be very grateful. We're North Americans. I think people all over the world are in the habit of tearing down people who are successful, and even more so people who are not successful. But ambition shouldn't be criticized as much as it often is. Yeah. So and so what's happened, of course, is especially in New York City, you have the Polish invasion, DMD and Polcom, who are supplying modules into the New York market via Skystone Group, and they've developed a number of projects and continue to do so.
Yep.
So just to quickly cover what happened with B2, they imported a technology from England, which is sort of popularly referred to as the Powerwall system, and it has the next slide really shows it. There's kind of a plate with threaded rods projecting up from it, and these threaded rods pass up through the hollow steel sections at the corners of the modules. And if I go back, you can see here a module landing on one of those fittings. And so, of course, this provides very, really, to be honest, very limited vertical tension capacity. So there's nothing to stop the building basically from blowing over in a high wind. Colloquially, that's the way to describe it. So the way that's managed, as you can see here in the top right of that slide, is there is a brace frame, and there you see a much better view of it, a brace frame, and that's the system through which all of the lateral forces are converted into vertical forces and taken down to the foundations. So the modules are tied into that brace frame at multiple points over the length of the building. And the very great problem that they had there was that the tolerances in the brace frame, the tolerances in the modules were distinctly different. And even the modules themselves were not terrifically accurate. So there was an enormous amount of shimming and cutting and packing and adjustment and monitoring and surveying and everything that was required to erect this building. And consequently, a lot of cost and delays resulted from that. So I take some credit, whether it's justified or not, for introducing the idea of tolerance accumulation to the discussion about modular construction, tall modular construction. And I created this slide during the Vectorbloc period to explain that. And I think it's, you know, what's interesting is if you looked at the facade of B2 when they got to about the 10th floor, there really was a 1 inch plus variation in the height of the stacks and large gaps starting to show up and so on, which were attributable to this issue. And so the conclusion was that you needed a precise, geometrically predictable system in order to control the dimensions of the modules in all three axes. So you knew where you were as you went up. You knew where you were as you're manufacturing the frames. You knew where you were as you're assembling the frames. You knew where you are once the frames are assembled. And that was the genesis of the Vectorbloc system. So it preserved the hollow steel section structural concept that had been developed by Arup and manufactured by Banker Steel, but it added this steel casting at the corner, which provided all of the locating features.
Yeah.
And you can see there the green, the bright green component is the gusset plate, which provides the horizontal capacity to the system. So that's the horizontal link that gives you your diaphragm action and so on.
So it limits the need for a secondary frame in this case.
Well, so I believe I hope there's a slide that comes up that shows how this system is adapted to provide the lateral capacity within the modules. But essentially, by installing diagonal bracing, tension compression bracing in a frame made with a system like this, then the forces the lateral forces are handled within each module. And as you stack the modules, you're stacking the diagonal system of the building.
As well.
Yeah.
It's a really interesting concept, and I remember seeing it years ago, Julian, when you were starting to market this and discuss it at various conferences. One thing it got me thinking a lot about was the notion of, for lack of a better way to describe it, the innovative thing about Lego, for instance. I know modular is often likened to Lego, but I'm going to maybe take a different tact on this. Interesting thing about Lego is the standardization of the connection, right? That allows you to have infinite variability within a system. So you might describe this also as like the 110 outlet, right, in North America, which would be you can take any device and plug it into the wall and it works, right, because of the standard plug, the standard outlet. And in many ways, the problem with construction over the years when we start talking about standards is people think that means, well, you can't have any variability. But what you've tackled is, no, the standard is the connection. It's the way in which the elements come together. The variability is everything else that you want to do around that connection. Which is, it's really interesting. It's not unlike what Buckminster Fuller thought of in the unistrut system, or I'm sorry, in the universal joint system, but it never could be really developed because it has so many limitations. This is tied directly to a method of construction, which is pretty innovative and solves some.
And already standardized.
Yeah, you've hit the nail on the head. Actually, there's two elements to the system that are, and they're interdependent. So one is the existence of a specific locating feature, namely that vertical pin, and the hole in the bottom of the next block up into which it fits. And the second is the fixtures which position those blocks in three-dimensional space so that when the tube that spans between the blocks is welded in place, you get an accurate structure, and it's consistently accurate.
Yeah.
So and it's kind of like, you know, they say that Henry Ford had to invent the car, but it only worked because they also built the North American road, the global road network. And it's the same with railways. You know, without the railroad, you can't have the rail, you know, the engines and the cars and everything. And it's the same thing here. Without the jigs and fixtures, you can't make a repeatable box that will dependably interlock with another box. So if you look at the video of the Cheatham Street Flats project in San Marcos, Texas, going together, which is the first large-scale building built with this system, the actual assembly of the building was extremely rapid, and the interconnection of the modules very, very dependable. And I'm happy to say that the system worked clearly and enabled that.
Yeah.
You're right about Lego. You know, I've often in those same conversations about the concept, I've said, can you imagine, you know, cheap Lego, badly made Lego? It wouldn't be any fun to play with.
Right. No, and it presents an interesting solution to this idea that if we are trying to automate factories, right? Ivan and I have talked a lot about appropriate levels of automation across the modular industry. What it presents is an opportunity to leverage robotics for welding, which has been a challenge in the past. And now you have, you know, three-dimensional location where those robot welders can come to and actually perform that operation. It's pretty powerful.
Yes.
But also the other thing is the Achilles heel of even highly precise, highly automated systems is the connection. So some of the, you know, systems in the 60s and 70s that had high automation in the first round had the same problem with the connection. The connection itself, which is actually the part that happens in the society, is the most chaotic, it's the most complex, sometimes received the least amount of standardization and thought, which seems like a kind of a strange contradiction in terms when you're, you know, the factory space is controlled, the construction space, the site space is not. Wouldn't you think that the degree of standardization and would focus on that, you know, where the rubber hits the road, which in this case is where the mods connect.
Yeah, and by the way, you know, there's a classic case here as well of how a whole bunch of things have to converge for this to work. You know, the ease of making weldable steel castings, because this isn't cast iron, of course. This is steel, and it has to be weldable. The precision of the hollow steel sections themselves, the laser cutting of the gusset plates, the machining of the locating pins and everything else, you know, the existence of the robotic systems, all of these contribute to the feasibility of an approach like this. And were this to be done manumatically, let's say, you know, it would not be as cost effective for sure.
Yeah. That's great. Oh, Julian, yeah, why don't you keep going and we'll look at how this is played out.
Yeah, just by the way, just to, you know, we've covered this, but, you know, to be clear, again, the role of what's now called Industry 4.0 and so on is abundant here. You know, we leveraged the 3D model of the Vectorblocs in order to do all of our simulation work prior to commissioning the castings and so on. And we did fully instrumented testing at the University of Windsor to provide, you know, to get all of our ultimate limit state information in the bag and so on. So that company's clearly taken off, and it's now the dominant player actually in North America. And so, you know, going back to the mountain and you know, doing the you know, the guy on the, you know, stroking his beard on the mountaintop with the, you know, the icy winds on the side of his head and rethinking everything. And, you know, my former parent company, the Walters Group, created and owns an entity called iSpan, who have a really, really beautiful I-beam shaped rolled steel section. It's basically like a, this classic C section light steel framed joist, except that both the top and bottom flanges are T-shaped, and they're double rolled. So they're putting steel where it's needed and everything else. Really nice. And I saw that there's a lot of innovation in this space, and I started looking at the masses, and they're routinely building buildings that are in the 11 to 12 pounds per square foot for the steel. The light steel framing, and that's very, very efficient, and the costs are very low.
Mm-hmm.
However, the state of the art in that industry is some really super dodgy welding that you really can't call real, and as evidenced in this image here, and this is unfortunately ubiquitous. You see an enormous amount of this, and I kind of actually even can't imagine how this is all possible, and yet you see a lot of it. And so we sought to develop a system that is, again, coil fed. The raw material is coil.
Mm-hmm.
Coil is a very, very efficient raw material for the mass production of structures. But where each member is utilized optimally in its role. So you see here that the rim joists and columns, so the rim joists obviously are, loaded horizontally and bending and tension and compression and so on, depending on the forces on the building. The columns obviously in tension and compression. And so we've conceived of them as 1/4-inch material as the baseline, trending down to 1/8 and up to 3/8, depending on the loading. And the floor system, the horizontal system, is entirely light steel framing. This is highly efficient. So the skeletal structure of the building has essentially outline frames made of light steel, made of sort of cold form steel, in other words, break form steel, and horizontal systems made of roll form steel, the light steel framing. And but an essential feature of the concept, which has been around now for decades, is this idea of precision locating features, just like those conical features on the power wall system, or by the way, the knuckles on the corners of ocean freight containers and so on. So you need something that guides the module very precisely into its final location, but in this case, and some means of providing that horizontal connection. So we've been able to pack all of that into an extremely dense 4-inch by 4-inch space. So the entire connection, the vertical locating, vertical tension, and horizontal capacity all occurs in a essentially between two modules in a 4-inch by 8-inch space, 4 inches by 4 inches on the top of each one. And so this confers obviously an enormous number of benefits. So here you're seeing that the vertical locating feature is also the vertical tension capacity, is also the horizontal shear capacity. That connection piece, which has the tapered sides to it, provides a solid clamping action for the horizontal connection. So all in all, this is a very, very nice solution to the provision of vertical tension, horizontal shear, horizontal diaphragm action, and precise location. And there's a benefit here, which is of course with those very wide, the typical column. We can build these with 4x4 columns, but you'd have to provide lateral capacity through some other means. If you bump those columns up to 4x12, and you look at the ribbing that's going on here, the stiffeners and so on, and you actually have a significant amount of moment capacity in the connections, which gives you the lateral capacity that's adequate for low-rise buildings. So we're solving a ton of problems all at once. I want to dive into the floor joist a little bit. So your typical connection between a light steel joist and the rim joist is essentially a sheet metal angle with a ton of Tech screws, a ton of self-drilling, self-tapping screws into it. There's other systems which are essentially an ear bent out of a cutout in the rim joist and fastened using mechanical fasteners to the joist. The problem with all of those is that it's actually a very weak connection in this manner, and the fixity between the joist and the rim joist is very poor in the rotational mode. And there also isn't really a lot of tension capacity either. The only mode in which it's strong is in shear.
Mm-hmm.
And so we had to come up with a way of joining the joist to the rim joist so that they couldn't be pulled out, pushed in, sheared, or bent. And so that's where this approach comes in. We found that if you try if you apply a moment to a light steel frame joist, then all the force goes onto the fasteners and they fail in shear or they tear through the metal. So by dimpling the light steel frame joist like this and then clamping it between two plates, we actually achieve a full moment connection between this sheet metal part and the rim joist.
That's interesting.
And this is absolutely key to developing the torsional stiffness that you need in a module floor assembly. And the other thing, I suppose I should have a circle here. I don't know if you can see my cursor, but where the tab of that fixed plate goes through the rim joist, that's where the weld goes. And it's on the inside face of the rim joist, and therefore does not warp the rim joist in an undesirable way or, cause a big bow in it, and so on. So, we've resolved how to connect basically a sheet metal part to a structural part by clamping and still achieving the fixity that we need for a modular structure. And it's all 2 bolts and cheap. So that's really we've reduced the chassis really to 3 repeatable components. There's the light steel framed floor and ceiling framing, the outer horizontal members, the rim joist, and the vertical members, the columns. They only require a small work envelope for the robotic operation. The parts are easily detailed with lasers and so on. So it's really a very straightforward system to produce. And of course, so I think an important point worth mentioning is that assembling those components to make a module frame does not require any fixtures. So you receive a kit in the plant, you need a flat floor, the parts bolt together, and you've got a square true module frame in a few hours. Say four workers with rolling ladders and maybe a few genie lifts can put one of these frames together. And it's inherently square and true because the parts coming out of the plant are inherently square and true. Yeah, and that's so we've run a bunch of engineering simulations at this point with increasing levels of detail. So as usual, we concentrate on structures that are not optimal. Tall, narrow is a worst case scenario. It reveals your issues. So you see here an early run on a tall, narrow stack of 2 wide by 10 high. And you can see that only with the 1/4 inch material throughout, only in the lower floors do we even start to see any of the diagonal bracing over tensioned or over compressed. So it's obviously a very simple matter to bump that up. And by the way, red in this case just means 100%. It doesn't mean actually fail. And that's 100% of a factored load. So what this really tells us is that we can lighten up our steel in the upper floors significantly. So, 12 pounds a square foot isn't even, we don't even need to be that heavy, interestingly. So for low-rise structures, we believe we can get under 10 pounds a square foot. So,
Julian,
and then another, yeah, please.
Well, have you been doing any, on this particular solution, have you been doing any testing, live testing of these connections yet?
Questions like that are always terribly embarrassing at this point in the development of a company. It's like, well, like, have you actually built anything yet or even tested anything yet? And the answer is, of course, no, we haven't. And so I suppose the conversation ends here, right?
No, no. I just saw in your last example you went and did some testing at the university. I just wondered if that was the next stage in some of this. So.
Correct. Yes. So you're absolutely right, and it speaks to our business model. So our business model is we intend in this iteration of our efforts in the field of modular intellectual property development to be strictly a licensor of intellectual property. Okay. So we develop these systems, and then we seek out entrepreneurial companies who want to deploy them. And the fees we get from those companies fund our work. So at this point, we've had adequate funding to get to this phase, and we've only just signed on enough people that we can take this to the next phase, which is, of course, full-scale prototype chassis and destructive testing.
That's interesting to compare to the experience with the B2, where in some, I mean, maybe not, but did the B2, the B2 tower and its problems, did that give you a certain kind of experience, not as a kind of laboratory in the field that allowed you to think about some of those connections differently in a way that a kind of computer simulation may not always be able to do, or even a lab in a university?
Yeah, super, super good question. I mean, very well articulated question. So there's no question that multiple factors are coming together to make this exercise far easier than it has ever been. This whole cycle of conception, development, testing, deployment, it's been the focus of companies like Dassault Systèmes and Autodesk and so on to develop the tools that allow people like myself to go through those cycles faster and faster and faster. And so we're taking full advantage of that. All of this work is done in SOLIDWORKS, and so we're able to perform simulations and so on, and predictively analyze our work. But additionally, I've reviewed over 100 patents to get to this point, and a large number of scientific papers, from the civil engineering, structural engineering community. And so I'm able to, it's the old standing on the shoulders of giants thing. That's that's really, really helping us a lot. So we understand the loads that transmit through these structures very, very well. We understand how to achieve the precision, what's realistic and what isn't in terms of the machines that process the components. And so we're able to get much, much closer to a realistic structural scheme without having to resort to testing. And in fact, we conceive of the testing now really as verification rather than development. Yeah. So it becomes a question of bonding and insurance, right? More so than it is a question of product development. We're very confident in the product development process because of the strength of the tools that we're using in it.
Because I guess one thing we've seen, for example, it's interesting when you showed that, the use of, we went from sort of structural steel to light gauge steel. So in the Japanese context, there's a lot of, most of the modular we've seen there, and the panelized prefers to kind of avoid structural steel. It's lower scale and lower density, and works with light gauge steel, partly because it's cost, but also partly because there's a lot of knowledge in the auto industry with light gauge steel and almost none with structural steel, but not just in terms of abstract knowledge, but in all kinds of banal practical issues about handling the material, about weight in factories, all kinds of things that go outside of the realm of pure structural engineering, get into the realm of logistics and assembly and all the problems. A lot of the problems that the B2 had with tolerances went beyond. Also, engineering-wise, it made sense. And when you got to the field, the crane operator couldn't quite get some of those things to work. And so again, it's just like how, anyway, it's interesting because it seems like that project, and I agree with you, I think it's worth lauding both for C. Ratner and Shop for taking the risk, even because that project in a way in the field created a kind of experiment in a laboratory condition that we often don't get, no matter how well we set out the CAD models, the BIM models, and even how well we set up material testing laboratories. That kind of trial and error, which is built into the industry in other industries, the car industry. iPhones are not just made in factories or in laboratories. They're consumers drop them, and major things happen in that iterative process. And because construction is so capital intensive and so risky, anyway, so it's just interesting that the B2 Tower has that. I think that's something that maybe it's worthwhile, and I'm just wondering, how do we build that into?
Well, this is. I'm impressed by how far we're going and how quickly we're getting there. So it certainly has struck me for years, for decades now, that it's a shame that the proprietary nature of much of the construction industry and the invention industry and so on, it actually serves to stifle development.
And evolution.
And Google, for instance, is accused of being an IP hoarder, a hoarder of IP. And so we've also made it central to our company. As you see, our materials are very explicit. We don't try to hide any of the details from our potential customers and licensees. And in fact, it's a huge part of our vision that our licensees, in fact, will be. We will gather knowledge from them. We will regularly, we will organize meetings among them to share knowledge and experience and feed their knowledge and experience back into the product development process. So rather than having, it's a term I've used before, IP islands, where every company is an IP island and defends its IP vigorously with NDAs and everything else, we want our system users to actually join forces, share their experiences, feed them back to us, improve the product, and redeploy the improvements. And that's part of being, part of the new enterprise will be to do that. So.
And do you think that the fear of IP sharing, often it's described as, we've invested so much money into the product, into the development, but isn't it also, and it's genuine, I understand it, but not wanting people to find out how problematic sometimes patents are before they're really tested? Isn't that another part of the kind of fear of sharing these kind of innovations before they've gone through kind of trial and error, repetitive trial and error? I mean, that's what I think is great about sharing it and having different platforms in the field go through different feedback loops at the same time. I mean, that seems like a really smart approach, but because we keep finding this in the industry too, that whether they're low tech or high tech, IP is always described as if, this is my special baby, I've put so much effort, I've put so much into it. And then we often find, as kind of outside observers, well, often it's just the fact that you don't really everyone's afraid of the B2 situation, but we need to fail in order to succeed. I mean, that's how we get to, there's no other way to get around it, no matter how good SolidWorks is.
Yes, I agree with everything you're saying. And we're of course in the thick of it yet again.
Great.
Yeah, exactly. We're in the thick of avoiding failure. But so by the way, so this slide here, this slide here speaks quite directly to what you're saying. So Polcom, DMD, Tide Vision in the UK, Ayrshire, a large number of people have sought to emulate in the frame in the frame of the modules the performance of an ocean freight container. So an ocean freight container, has this continuous load-bearing wall, and when you stack them, the loads are moving through the entire side wall of a stack of containers. And that's really a bit of the miracle. That's how they, can use as little steel as they do, and yet every one of them can have, 40 tons in it and be stacked 20 high and so on. And so the idea is multiple vertical load paths, of course. So this is the secret behind projects like Croydon. I was very excited to attend the talk by the fellow who is driven the engineering on those projects. He was at World of Modular this year. I apologize if I don't remember his name immediately, but he's from Ireland, and you probably know him. And so we have integrated that concept into one version of this structural concept. So these are modules that have, let's call it insignificant diagonal capacity and enormous vertical capacity. And so these are well suited to buildings in the 20 plus story range, 30 story range, where you provide all of that lateral capacity through the brace core. So this is certainly something that, a popular idea that we've borrowed from multiple people and integrated into our approach. And you cannot consider this proprietary. This is not a, this is effectively an industry standard approach.
Or it should be.
Or should be, yeah. And we've just, well, by the way, this is, there's a number of North American modular producers, some of whom are gone from the market, like Coleman, who promoted this in their tall versions, their tall modular systems. So they didn't go for a point-loaded system where the forces are taken out to the columns. They went for a ubiquitous, like a load-bearing wall system.
Right.
Yeah.
Yep.
So and to cover a couple of other things here, just so to get them on the record in this call, because I think you'd be interested in some of the other things we're working on. So the cost of all of the people that swarm on the building, even after the modules are placed, is very significant. So we've sought to reduce the crew size to the maximum extent possible. So the first of the innovations that delivers this is what we're calling the plug and play capacity. So you picture and you're leveraging the precision of the modules. So as the modules come together, the vertical locating features, force them into alignment, and now they're dropping squarely one into the next. And so that opens up the possibility of having actually the water connections, the sewerage connections, the vent connections, and the electrical connections being made at the point that the modules contact each other. And so this eliminates the need for access covers and people to get into those spaces to make these connections. And, so the initial reaction of a lot of people to this has been, you got to be kidding. That's completely impossible. Never heard of such a thing. That'll never work. And then they'll, grumbling, they'll go off and snap their garden hose together and start watering their plants. Or, if they're shop types, they might go and connect an air tool to an air line. and we say, that Bowron guy's an idiot, while snapping the two pipes together and watering the lawn. And, and so, by the way, power over Ethernet connections and the connections that are found ubiquitously in data centers, on the back of the racks of electronic equipment, there are fittings exactly like this. So you slide the server rack into place, and across the back plane are all of these sorts of floating modular power connections. So this is an absolutely feasible approach. And we've done math that shows that there are, it's costing $2,000 to $3,000 per module to make electrical and plumbing connections, and another $1,500 to $2,000 per module to make the structural connections. And so to that end, we've also developed a system that has an autonomous mechanical connection between the stacked layers of modules that leverages the live electrical connection at the moment of setting the module. So you actually picture a module being placed and the electrical connection being live upon placement. And now you have the ability to operate an electric actuator, an electrically driven actuator that drives a pin into a link and connects the module to the structure. And so now, the thing can't be blown off, can't be toppled by a wind. You may have to go in and supplement it later with additional mechanical connections, depending on the height of the tower. But at the very least, the module is safely locked into the building, and everybody can go home and get a good night's rest. And so these two elements, the plug and play electrical capability and this semi-autonomous building assembly, are a component of the IP that we're developing for the next tranche. So the current block of knowledge is the structural system, and these are to be added over the coming years.
Julian, we've run out of time, but I want to thank you for joining Ivan and I on ModX Voices. Oftentimes, Ivan and I, we hear in the offsite industry and have participated in projects in which people claim there's very little IP in the modular space. And in certain portions of the modular industry, that's true. But what you've shown us today is that there's plenty of innovation that is not just IP protected, but is able to build with other partners a more sophisticated solution to what we are seeing, which is a maturing of, finally, a maturing of the modular sector to produce, buildings of sizable scale. And you've been incredibly instrumental in that process. And we're going to see, I think we all know that we're going to see modular take off here in the next 5 to 10 years. And you're certainly going to be continue to be a leader, but have a great mark on this industry. So we thank you for that incredible offering, and thanks for joining us today. We really appreciate it.